So today we're joined by Dave Wood from JBA Risk Management. Thanks for joining us, Dave. How are you doing?
Yeah, good, thanks. Yeah,
Good.
pleased to be here.
Yeah, great. So would you mind giving us a little bit of background on yourself and also an introduction to JBA?
Yeah, for sure. I'll start with JBA. I think it's easier to start with JBA.
Of course.
So we're JBA Risk Management's a flood data and flood risk model provider. We've been around since 2011. And so I joined later on than that. I joined in 2016. But it was formed because the founders, using some technology innovations around flood simulations, produced the first national scale flood maps at high resolution, like 5-meter resolution flood maps. And so these became the gold standard for assessing flood risk in the UK and London insurance industry. So off the back of that, JBA Risk Management was formed, and they went on to produce maps for the whole globe, and we've got high resolution flood maps for US and Europe and Australia as well, and also produced catastrophe models as well for assessing portfolio level risks. So that's the formation of the company. Yeah, we're getting bigger now. We've got about 130 people with offices in Singapore. We've just opened one in India. We have someone out in the US as well. And so in terms of my background, I guess it's a little bit unusual for the sector because, well, my background's chemistry and pharmaceutical research, which I'll comment on in a moment. So what I've been doing for my career is generally focused around data science and modeling and software platform development. So at JBA, well, I joined, I kind of oversaw some of the software development outfits, and then went on to oversee the product development division. And then just over a year ago, joined the board and took on the managing director role, which is what I've been doing for the past year. So, yeah, in terms of my background then, before JBA, I worked in the pharmaceutical industry for a little over a decade. Yeah, after a decade, there was huge contractions in the industry, lots of redundancies, lots of job chasing. So with a young family, got tired at some point and looked elsewhere and ended up at JBA. That's where I've been since.
Oh, awesome. Really interesting. A couple of things I'd like to pick up on and I guess ask some questions around. Firstly, I mean, you've mentioned opening a few offices in various different places in the world, Singapore, India. So what does it actually take to assess risk, flood risk at a global scale?
Yeah, well, I think our maps, high resolution maps, are basically core to everything that we do. Like all of our product lines are based on that. And so we've got a team that works on producing new maps for new regions. They're sort of experts in the hydraulic modeling. Some of the areas that I worked on whilst I've been at JBA has been setting up our online services, so web platforms and API suites that people can hook into to assess flood risk. So yeah, really, it's about scaling up that modeling activity and scaling up the team so that we can, model at that global scale, essentially.
Great. No, thank you for that. And the other thing I wanted to touch on, it's interesting, we speak to a lot of various data providers and specialists in different areas of risk data. So, and they all have different backgrounds, and yours in pharmaceuticals was particularly interesting to me. So what are the parallels and data challenges that are shared between pharmaceuticals and catastrophe modeling? And are there any specific learnings that insurers can take from the pharmaceutical industry that they can kind of implement when they approach data models and simulation?
So I think, yeah, when I moved from pharmaceuticals to the insurance sector, I think one of the things that surprised me was the crossover. I expected it to be a more abrupt transition, but there's a lot of common techniques around. I mean, it's all building models, it's all software development and data science tools and statistics. Yeah, there's some interesting parallels actually, because in the early days of my career in the pharma industry, there was an ongoing debate around, data derived and machine learning based models, because my PhD was in machine learning originally. That was one camp, if you will, and the other camp was all about the conceptual models and well-crafted parsimonious models that could be easily interpreted. So back then, there was a lot of debate over, what produces the most reliable models. Now, the interesting thing about the pharmaceutical industry, which is different to the insurance sector, is that we had a really rapid feedback cycle. So we'd build models and we'd use those models to select new molecules, and you could get them ordered and get them synthesized and tested, and you'd get pretty quick data and feedback over the reliability of the models. And that's quite different when you're dealing with extreme weather events that only come along so often. That feedback cycle is really quite helpful. But the interesting thing back then, because we had that feedback cycle, pretty quickly we discovered that, the machine learning approaches, techniques were around like random forests at the time. And these, you would just pile all your data in and expect the model to synthesize that data and come up with something useful. And those kind of approaches won out back then simply because they were more predictive, they were more accurate. And so whilst, there's always a place for the conceptual models. And if you want to understand the underlying mechanisms of whatever it is you're modeling, then those are important. But in terms of just prediction accuracy, even back then, those machine learning and data-driven approaches were proving very effective. And that's kind of led on over the past few decades to these massive neural networks that you're seeing behind, ChatGPT and other large language models, right?
Yeah, absolutely. And it sounds like in risk and insurance, there's a real opportunity to benefit from that, as you say, particularly in, I guess, climate risk, flood risk. There's a less reliable cadence of events to feed information back in.
Yeah, sure.
And so utilizing that kind of predictive machine learning AI approach sounds like a real opportunity.
Yeah, well, there's a lot of data floating around, especially within the insurance companies, right? And so these techniques that make use of all that data helpful.
Mm-hmm. I'd like to ask you a little bit about that later as well, because I imagine you have some really interesting thoughts on that. But to move on a little bit, historically simulating weather has involved complex, computationally heavy models, physical models as well. We're now seeing quite a significant shift towards deeper neural networks. Can you explain how this transition changes the speed and scale and accuracy at which you can run global simulations?
Yeah, so this relates to work we've been doing in the company recently to build. Well, let's start with the catastrophe models, right? So we produce catastrophe models, and these need to have a huge catalog of possible weather events behind them. And we've been exploring ways to generate those catalogs of extreme weather events. So in terms of weather simulation and forecasting, I mean, the gold standard there has been numerical weather prediction models. Now, these are kind of really complicated mechanistic models. There was this really nice presentation by a guy called Thomas Hamill, actually. It was at NVIDIA's GTC conference. He's at the weather company. I think he's Chief Innovation Officer. And he was exploring, these data-driven approaches compared to the well-used numerical weather prediction models. And so these numerical weather prediction models, they'll have a huge number of modules and components, that capture different elements of what goes into weather patterns being quite chaotic. And so in a way, well, they work really well. They're reliable, but they're also quite computationally heavy as well. And so when we're trying to generate weather patterns, we could use numerical weather prediction models. What we're finding is that just the the computational heaviness of these things means that we can't use them extensively. So what these deep neural networks allow us to do, so these deep neural networks used for AI weather models, all the data goes in, the neural network crunches all the numbers and it models the dynamics. So in a way, despite the fact that they're these vast neural networks, they're actually conceptually quite simple. It's just data in and data out. And they've also got the advantage of being much, much quicker of the numerical methods. And on top of that, because it's conceptually simple, as we get more data inputs, we can get data from drones now, we can get data from satellites now. It's easier to pull in these new data sources into the model and have them incorporated into the weather simulations. So these things are like, thousands of times faster than numerical weather prediction models. And that allows us to run longer simulations, more simulations, and really explore the range of possibilities there.
Interesting. Sounds like there's almost no drawback in that aspect. You mentioned them being thousands of times faster. It sounds like they're perhaps quicker to implement, quicker to derive value from as well, and perhaps benefit from the whole kind of economies of scale approach that we're getting, because I presume we're leveraging existing LLMs, OpenAI, Google Gemini, that kind of thing to drive these neural networks.
Yeah, I mean, we're using them off the shelf. Like the collaboration we've been doing with NVIDIA is using their ForecastNet 2 model, for instance, and it acts as a weather generator for us. So in that sense, it's easy to use and it's all compatible with the kind of computing resources that you have in the cloud. So they're easy to set up, and well, I wouldn't go too far and say they're easy to set up, but relatively speaking, companies like us can hit the ground running with these kind of models, whereas the numerical weather prediction would require much more computational resources to do what we want. So yeah, and these things, I think in terms of the accuracy of forecasts and predictions at a global scale, they have a kind of 25-kilometer resolution. At that kind of level, they're working really well. In terms of the forecast skill, they're up there alongside typical numerical weather prediction methods. In terms of the more local scale, which can be important for certain weather patterns, we're seeing rapid progress now. But they're not up to the level that you can see with the numerical weather prediction models. But it's a moving target. You see, the technology is advancing quite quickly.
Mm-hmm. Yeah, it seems like a really kind of complex problem to solve, particularly for insurers, reinsurers, etc., to consider, because they don't have in-house expertise on the technological side of this. Like, they understand climate risk, they understand flood risk, but how do you build a model that can predict what's going to happen in the next 1 year, 5 years, 25 years, and that can do it in a reliable sense? And I think a lot of what you just mentioned highlights the importance of approaching a buy versus build mentality correctly. Trying to build everything that you've been talking about in-house for an insurer is not really a realistic prospect, and buying everything is maybe less scalable. So we kind of think about it from a buy to build perspective, and you kind of select the components you want to buy and you assemble them and you build a tool that can support your view of risk. And yeah, it sounds like that's definitely an aspect for insurers to look at buying and implementing, integrating into their existing systems. So insurance has traditionally relied on historical records to predict future risks. However, deep learning allows us to model unseen weather patterns. How does a model simulate a weather dynamic that's never historically occurred? And why is that capability critical for understanding a modern risk profile?
Yeah, okay. So this relates to an area of work that we've recently published, actually. We've got a blog on our website talking about generating unseen patterns, and we've published a paper as well. It's called AI-based seasonal large ensembles for fluvial flood risk. So I'm just going to plug that. It's a nice paper that's been written by a couple of our members of staff called John Ashcroft and Alison Poulston. Now, what we did in this published study was we used these weather generators and we looked at the Elbe Basin in Germany. And specifically, we looked at winter 23-24. Now, this season was of interest because it was quite a significant flood season. It was also interesting because it followed a very wet summer. And so there's all sorts of interesting questions around what they call counterfactual analysis. It's what could have been, did we get lucky or unlucky that year? So we're using these weather generators to simulate 3-month seasons of weather. Now, because weather is chaotic, right? And these models generate the weather, well, they're based on the weather dynamics. And so we can generate, what we did was 1,000 different variations of that season. So you can create those 1,000 variations by using different start days or using different versions of the model, for instance. And because weather is chaotic, after a couple of weeks of the simulation, it completely decouples and you end up with completely different weather patterns. So we end up with a data set of 1,000 winter seasons for that Elbe Basin. And so what John and Alison have done, they've sort of demonstrated that we get, firstly, completely new weather patterns that we haven't seen before. We get new compound events. So some of the most extreme seasons in that sample were seasons that had multiple rainfall events throughout the season. And we see events that are more extreme than anything that's been seen in the historical record. So essentially, that sort of demonstrates that we can use these models to generate those unseen extreme events. And the data set that's produced, we can use after a lot of validation and analysis to understand what the risk profile looks like. And so rather than working from an observed record of, a few decades, we're working from those, 1,000 years of possibilities. So yeah, it's an interesting study.
It seems like it offers a much more realistic view of risk when it comes to climate data, because looking at historical data, I guess by definition, you can only factor in what's already happened into the future, whereas simulating in that way, it's all the possible kind of climate actions that might occur in the future and gives insurers a much better view of risk and all the things they have to account for when underwriting.
Yeah, that's it. So, I mean, if you think whenever a significant event comes along, you hear it often said, oh, it's unlike anything we've seen before. So in the observed record, if, a Category 5 hurricane hasn't hit a city, then a lot of the statistical modeling techniques that we've used in the past might say that the event, there are no Category 5s in that area. And so what this does is really flesh out the range of possibilities that are in there.
Mm-hmm. Yeah, just because it hasn't happened doesn't mean that it can't.
Exactly.
Interesting. So, I mean, we've kind of covered this a little bit already, but in catastrophe modeling, extreme situations can often be hugely impactful to the models created. And given that AI models can sometimes have a tendency to pull results toward the average, how do you ensure that your models accurately capture those vital data points without losing precision?
Yeah. It's a challenge. With any of these techniques, you do see that kind of regression to the mean, and you do see the extremes pulled in. For instance, we've used a certain technique. It's called LSTM. It's long short term memory networks, and they're good for time series. And, we've used those for modeling what happens with rivers. Now, all the publications show that these techniques are, best available. They perform really well when you look at the prediction accuracy. But The challenge is that we're interested in what happens at the extreme, and that's where least data is. And so you get that regression to the mean effect. So there's all sorts of techniques that you can use to counter that. You can put loss functions into the neural networks that protect against this. There are adversarial learning techniques that sort of help you to make sure that you've got the extremes. So, and then ultimately you can also manage the distribution yourself through post-processing and bias correction techniques as well. So I think it's important to understand that regression to the mean effect does happen, and our scientists at JBA, that's an area that they're working quite actively on. Now, what we did see, on that paper I mentioned with the Elbe Basin study, we did see that the weather generator is able to generate more extremes. We're using a technique called huge ensembles. Like, that 1,000 ensemble set means that you do see those outliers and extremes in there. And you can sort of validate to make sure it's picking those extreme events. But yeah, it's an area that requires careful validation and attention when you're building these models.
Mm-hmm. So it sounds like having it in mind and having the techniques to address it and account for it is the kind of key point. And you mentioned a couple of those techniques. When it comes to the outputs of using AI in risk management, there's often skepticism, and specifically that pertains to the black box problem. Like we don't understand what's going on within the LLM. So what's your philosophy on validation, and how do you move from generating a result to actually trusting it enough to base an underwriting decision on it?
Well, I would say that there's that famous quote, isn't there, that all models are wrong, some are useful, right? And I would say that you should never just trust a model. It doesn't really matter the underlying technology, whether it's a neural network or a conceptual model or anything else. You shouldn't just trust the outputs of the model. And that's why, the transparency in publications and the validation is so important there. And so, comparison with previous extreme events is helpful. And there's various other ways we can be confident that the extremes that we're getting are right is all important.
Mm-hmm. I mean, it's hypothetical in nature, isn't it, when you're kind of modeling what might happen in the climate. And it sounds like anything really, the key to trusting it and making it reliable is validation with other data, other real data.
Yeah. And you've got to remember as well that these models tend to be components of broader systems, and all these components come together. And so the most important thing is that we can explain the input and the uncertainty of each component, see how it feeds through the model and produces a result that matches the expectations that we're looking for.
Mm-hmm. So transparency, explainability, and validation seem like the kind of pillars of that.
Yeah.
So scaling AI solutions has also been a historical challenge, particularly in insurance, but it requires significant computational power. So for leadership teams looking to modernize their modeling, how should they approach the cost-benefit analysis of investing in high compute AI models versus sticking with simpler traditional statistical models?
Yeah. It's one of the trends of the moment. The technology's all moving so fast, right? And accelerated computing technology, it's every couple of years we take a massive step forwards in what's possible, and often a massive step forwards in the costs of the computing hardware as well. And similarly, the models that we use are updated regularly as well. So it can be quite challenging to keep up with the pace of that technology development at the moment. I think key to all this is because, I can be a bit of a sucker for technology, to be honest, and it's tempting to, go all on the biggest models and, the most expensive hardware and all the rest of it. But ultimately, it comes down to that sort of cost-benefit assessment. And I mean, let's say that a bigger, more expensive model was better, then you've still got the question of whether that's supported by everything else that goes into the model. So, you could be putting a Ferrari engine in there, and if there's a lot of uncertainty and limitations in the rest of the model, then it's kind of wasted. So you've got to ask your question about whether, the latest state-of-the-art, most advanced models and hardware actually produces that valuable improvement to the outputs, right? Mm-hmm. So you've got to make sure that in terms of the cost-benefit analysis, that it's supported really. But also, I think we always try and start with the simplest approach. I think the real costs come into model training at the moment. Running these models, it's not too bad. They're not too expensive to run. They're much cheaper than numerical weather prediction models. But if we get into training our own models, our own downscalers, then that's where you can start racking up tens to hundreds of thousands of compute costs. And so we've always got to consider whether there are simpler options, whether there are simpler, downscalers or statistical methods that can be used instead. And we always try and start with those simplest approaches. Mm-hmm. So it really comes down to the impact in, well, I suppose, the outputs of the model and the user experience, and a balance with the costs.
Absolutely. And it seems like for insurers and what that means to them, this brings us back to the choose carefully what you try to build versus what you buy, and also invest in digital transformation, in AI from a skills perspective, like to evaluate the benefit of some of these technologies we're talking about. Somebody internal is going to need to have a good understanding of them. And so, yeah, I think the skills piece is a big part of that conversation. So while flood is your core focus, the technology behind these simulations acts as an engine for understanding the physics of the world. How might these deep learning techniques eventually be applied to other perils to create a more systemic view of risk across a whole portfolio?
Well, they can, and they all are already. So the weather models that we're using, they're global models, and they simulate a range of weather parameters, and we're building on that to get rainfall and work out what happens with rivers as well. And so you're right that we're focused on flood, and that's our area of specialism. But when you've got a globally coherent weather model, and you've got the ability to sort of derive potentially high resolution weather patterns from that, and you can produce correlated perils, so we can link the precipitation to the wind and the impact on surge. We could also relate lack of rain to other perils as well, like drought or heat, for instance. So because we're basing everything on that weather simulation, we can start to look to derive those correlated perils and compound events potentially. So there are limitations to what you can do there, starting with a global 25-kilometer resolution weather model. It's not going to help with some perils, like it wouldn't help with tornado, for instance, which is really local scale. But we can sort of imagine how all this evolves, and how as the models get more sophisticated and higher resolution, then you end up with a generator that simulates all these perils, and we can derive everything from it. Essentially, you can sort of see that direction of travel. Who knows how long it's going to take? It could be decades, or it could be shorter than that. But there's that ability to see how you can derive all those other perils from the model.
Yeah, interesting. I've had a similar conversation recently, in that we look at data in its context, and want to use it for that one individual context. But I think there's a lot more creative uses for data that can be kind of generated from it. And it sounds like this is the same. There's benefits that can be translated into other perils that aren't perhaps specifically flood, and to offer insurers kind of greater insight into risk profiles and better understand how to underwrite particularly complex risks. So I've got one last question for you. It's a bit of a fun one. If you could change anything about the insurance industry, what would that thing be and why?
Yeah, sure. Okay. I think we touched on it slightly earlier, but I think one of the challenges for model vendors is model building is a scientific process, and any scientific process requires data for validation and, refining the model. The challenge is that the insurance companies tend to be quite protective of their data for obvious reasons. They see it as a competitive advantage. But that means when we're developing models, we're often working in the dark. We'll build a model, and it's only when we start, we've got the model fully set up and working, and we have a development partner who starts trying it against their portfolios. That can often be the first, feedback and validation we get, that the model is on the right track and built the right way. And that's really quite challenging as a model developer, because we're sort of working in the dark. And interestingly, there's another parallel with the pharmaceutical industry. The same thing was going on there. Pharma companies were always really protective of their data. And over time, there were these initiatives to produce open data sources. And these open data sources supported academic research and model builders within the sector, and a whole set of benefits from that. So in terms of what it would be great to see changed in the insurance industry, it's really that access to data. Because, if we had good access to data, then that would benefit us in terms of building models, and it would benefit all of our customers and the sector as a whole. So yeah, that would be the thing I would most change about the insurance industry.
That's really interesting. I think it kind of points towards insurers taking a less transactional and more partnership-based view with providers like yourself, because they stand to benefit so much. There's a huge opportunity to improve the quality of data and what's possible. And I think we see that, for example, in the LLMs that everyone knows, Gemini, OpenAI, they've progressed so quickly and so much because of the unstructured data source and open source data that is the internet. And I think that's a good kind of allegory for that. So thanks for joining us, Dave. That's been super interesting. A lot to digest. But yeah, I think the message you've left it on there, in that there's a huge opportunity to kind of drive competitive differentiation for insurers, is a good one.
Great. Well, yeah, it's been good. Thank you.
Thanks, Dave.